Hey guys, Miss Marusik here, and in this video we're going to be talking about the kinetic molecular theory of gases, basically a set of points that describes the way that gases should behave under ideal conditions, and then we're going to talk about the conditions that would cause us to deviate from those behaviors. So to start us off here, it says there are 5 basic postulates or points of the kinetic molecular theory, again, all which describe an ideal gas, if a gas is behaving perfectly according to plan. And the first of those points is that particles in a gas are tiny and their size is negligible compared to the average distance between the particles. So for example here, if I'm comparing 2 gas molecules, the size of the molecules themselves are very tiny in comparison to the space that's between those gas molecules. And to be honest, this picture doesn't even do that space justice. The gas molecules are way smaller than this, and that space between is way bigger than that. So that size differentiation is huge. And so because of that, we would say that the total volume of a gas is mostly empty space. If we were to consolidate all of these gas particles into, say, the corner of this container, it would take up a very little space of the container itself. Most of the container would be empty space. All right, the second point of the kinetic molecular theory states that particles in a gas move in straight line paths and random directions, and also at various speeds. So, for example, in the sample, all of these gas molecules would be moving at various speeds. So some would be moving much faster while others would be moving much slower, even though they're all at the same temperature. However, if I was to follow the path of a gas molecule, say the path of this guy right here, I would know it's moving in a straight line path, and it would continue to do so, say, until it bumped into the wall of this container, and then it might bounce off and keep on going in a straight line path until it bumped into something else, maybe another gas molecule. And then it could bump off of that and continue going until it bumps into a wall again. So again, it's moving straight line paths, and we don't know which direction it's going to go. It's kind of like if you've ever seen The Office. I happen to be a fan of The Office. There was an episode where at the beginning they were all sitting in their conference room watching the DVD logo bounce from side to side on the TV, and they were waiting for the DVD logo to hit into the corner of the TV, just in the perfect exact spot of the corner. And it kept on bouncing in those straight line paths in random directions, and they didn't know exactly when it was going to hit that corner. Basically, gases move exactly like that. So, all right, our next point of the theory is that particles in a gas collide frequently with the sides of the container and less frequently with each other. So for example, again, it is way more likely for this gas molecule here to be going in a random direction where it hits the wall of the container than just the sheer probability that it would go in a direction where it could collide with another gas molecule. Again, it's kind of just a surface probability at that point. So anytime those collisions occur, that is what creates pressure. So pressure is basically kind of how many collisions are occurring in the container. The more collisions that we get, the higher the pressure would be inside of the container. Now, one other note about the collisions occurring. We always say that those collisions should be elastic. What that means is that, let's say you had a fast molecule that bumped into a molecule that was moving really slow. So one had a lot more kinetic energy than another one. That fast one could transfer some of its energy to the slower one, so after they collide, maybe then they're both moving at a similar speed that's somewhere as an average of the 2 speeds together. Or maybe you have 2 that are moving at about the same speed, and after they collide, one's moving really fast and one's moving slow. But the total energy in that collision should remain consistent. The additive energies should total up to the original energy that we had. All right, another statement of the kinetic molecular theory states that particles in a gas do not attract or repel one another. They do not sense any intermolecular forces. What that means is that intermolecular forces are assumed to have been totally broken. There's no more attractions between those molecules, nothing holding them together at that point. They are free to move. All right, the last point here is that the average kinetic energy of all the gas particles in a sample is proportional to the Kelvin temperature of that gas sample. As we've already talked about, all of these gas relationships only are true in terms of Kelvin temperatures, but basically when that Kelvin temperature increases, what that means is that the kinetic energy of the gas particles is also assumed to increase. Remember, temperature is a measure of average kinetic energy. All right, so obviously all of this is explaining what happens when a gas is behaving perfectly according to plan. But as we know with most things in nature, not everything behaves perfectly according to plan. And so there are certain sets of conditions where these points become a little less truthful. And so we want to talk about when would we veer off, when would we deviate from these described behaviors. And so that's where we come down here with the deviation from ideal gas behavior. It says that gases start to deviate from the behaviors listed above if conditions encourage intermolecular forces to reform. If those attractions are starting to reform, that freedom to move is not as random. We don't see those elastic collisions quite as much. We don't have quite as much empty space. There's a lot of things that we don't see once those IMFs begin to reform. Also, anything that brings molecules closer together would also cause us to deviate from those behaviors. Either the gas molecules being very large or just maybe changing the volume of the container itself to cause the molecules to be closer together. So it gives us some situations here. It says, would intermolecular forces reform at high or low temperatures? Well, let's think about this. If I wanted to go from a gas back to a liquid, back to a solid, would I want to increase or decrease the temperature? Hopefully we realize that we would want to decrease our temperature at that point. So low temperatures would cause IMFs to reform. So what that means is if I have a gas where I start to decrease the temperature, as I'm getting closer and closer to that transition back to a liquid, I might start to see a few IMFs here and there reform. And if that's the case, then we're going to veer off from those ideal behaviors. All right, it says, would intermolecular forces reform at high or low pressures? Well, let's think about this for a minute. A high pressure would be when my volume is more than likely really small. I get a lot of collisions happening, a lot of interactions. At low pressures, I probably have some sort of really big container where those molecules can spread out and I get a lot of empty space. So the closer my molecules are together, the more likely IMFs would reform. So this one would be our high pressure scenario. Not only that, but if I have that high pressure and I get a lot more collisions, what that probably means is that more than likely my molecules are closer together, and so therefore I have less empty space than I normally would have. And so again, if my gas is not mostly empty space anymore, then that causes us to veer off from those ideal conditions. All right, it says, would you expect a substance with a strong IMF type or a weak IMF type to deviate more from ideal conditions? Well, again, we set up here, if conditions encourage intermolecular forces to reform, as those are reforming, we don't have as much freedom to move. And so a strong IMF type would deviate more from those ideal conditions because we're more likely to reform those IMFs. They were stronger to begin with, so it's a lot harder to break them, and so it becomes much more easier for those to reform. So if I was presented with two different gases and I was asked, hey, which of these gases might have more deviation from ideal behavior, if I look at the intermolecular force type, a lot of times that can help me to know which of the gases might be deviating more from ideal conditions. The stronger the IMF type, the more it would deviate from those conditions. So we've got kind of some summary statements down here about our ideal gas law behavior. It says a gas will deviate from ideal behaviors, as we said, at low temperatures and high pressures, or if the IMFs are really strong. Again, at these sets of conditions, our molecules are close together, and the space between the molecules themselves, what they take up, is no longer negligible. What that means is that the molecules are getting so close that our gas is no longer mostly empty space. Okay. However, our gases behave most ideally, most like the statements from the kinetic molecular theory, if we have high temperatures, low pressures, or if the intermolecular forces are weak. And the reason why is because ideal gases have molecules that are far apart, that they're mostly empty space. And these three conditions here would help to ensure that those molecules are far apart. All right, hopefully we're feeling a little bit comfortable now with the kinetic molecular theory. If you have any questions or need any help, please feel free to email me. Bye, guys.